Hey everybody, it's Monday, January 11th, and as you can see here in the aim today, our goal for today's video is going to be to answer this question: how are work and energy related? This is the first of a series of videos which now is getting us into the new unit, which is all about work, energy, and conservation of energy. And so essentially what we're doing here is we are going to be taking a look at a lot of familiar situations, a lot of situations that we've already looked at so far, but from a totally new perspective. And that really is the ultimate goal of this unit here, which is, yes, we want to look at situations which are familiar, but then we also want to extend them out to new situations because of the ability that this new perspective gives us. And so what you will hopefully realize is that when we look at old situations, we can recognize that this new perspective, this new approach, being the use of work and energy, will give us the same answers as the approaches we took to these familiar problems, but that now we can also extend it to a wide variety of other situations which we've already looked at. That's an important thing to realize. Now, as we go through this unit here, there are going to be a couple of questions that a lot of you are going to want to ask that are going to be difficult to answer. Because what definitely confused me when I first started learning about work and energy is I couldn't quite get a handle on what work and energy actually were. It's a good question to ask when you're using something to answer physics questions. Well, what is this? What am I actually doing here? We can't really give a good answer for that. But what we can say, at the very least, is that this stuff works. No pun intended. It gives us correct answers. And we know that when we apply it to situations that we're already familiar with, because we already will know the answer to a lot of these problems, but we'll be able to do them in a different way. And so I think what is important to realize about this transition here that we're making in this latter part of the year now is what we're really focusing on is modeling. We are now moving into the part of the year where things are less tangible. And what I mean by that is like they're not so obvious. Forces stuff, I think hopefully you would agree in retrospect, is pretty obvious. Newton was saying things like, if you push it, it will move. If you push it harder, it will move more. Things like that. That's pretty straightforward. Now we're getting into the part of the year where things are less straightforward. We are creating models for how things will work. Essentially what we're saying is we're making up this idea of work and energy, and if this were true, this is what would happen. Of course, the key power of this idea is that when we make this idea up and we say, if this was true, this is what would happen, is that that is exactly what happens. That said, I don't want you to get confused about the idea that we don't exactly know what these things are. It was probably put best by Richard Feynman, who is arguably the greatest American physicist, who said, it is important to realize that in physics today, we have no knowledge of what energy is. However, we know enough about energy to say what objects are doing when they have energy, what objects do when they gain energy or lose energy, and how that all fits into the broader picture of how objects move. And so it's important to realize while there are a lot of questions that we can't answer, there are a lot of questions that we can. And you're going to notice this more and more as we go through physics. They always say in physics that gaining knowledge in physics is kind of like blowing up a balloon, where the contents of the balloon are the things you know, and the surface area of the balloon is the things you now realize that you don't know. or you can't know. And so notice, as you fill up the balloon, you put more and more stuff inside the balloon, you learn more and more physics, you start to gain a broader realization of all of the things that you don't know. And so let's talk about what we can know and how we come up with these ideas. And where this discussion actually picks up, how we get into the discussion of work, actually comes down to basically the very last thing that we were discussing for new material, which is circular motion. Because when we were talking about circular motion, we answered a very, very important question, which was about how forces affect motion. Because when a force acts in a different way, it will affect the motion of the object in a different way. And so we looked broadly at three situations. We said, well, let's say an object is moving up toward the top of the screen with an initial velocity. And let's say a force acts on that object in that same direction. What's going to happen to the motion of the object? It's not a hard question to answer at this point. When the force is in the same direction as the velocity, the object speeds up. Pretty straightforward. That we'll call case one. For case two, we'll say here still we have an object moving towards the top of the screen, but instead of the force acting in the same direction as its velocity, what happens if it acts in the opposite direction? So, good question. What happens to the motion of an object when a force acts in the opposite direction of its velocity? And the answer here should be pretty straightforward as well. When a force acts in the opposite direction of a velocity, the object slows down. This is not really news. But the big revelation that scientists had, which enabled them, to come to the realization that work is an important concept for us to be discussing, really fits in with what we saw when we were talking about circular motion. Because when we were talking about circular motion, we said, let's imagine a situation where an object had a velocity in one direction and the force was perpendicular to the velocity. What happens to the motion of an object when the force is perpendicular to the velocity? And as we said when we were talking about uniform circular motion, when the force is perpendicular to the velocity, like the centripetal force is perpendicular to the tangential velocity, there's no speed change. Only the direction changes. And so now we have to realize an important thing. Situation 3, case 3 here, is fundamentally different from cases 1 and 2. They just are. Because when a force is acting in the direction of the velocity or opposite the direction of the velocity, the speed changes, and when it's perpendicular, it does not. And that's the key distinction. We need to come up with an entity, a physical quantity, which differentiates cases 1 and 2 from case 3. And as it turns out, that physical quantity, which differentiates cases 1 and 2 from case 3, is work. In order for work to be done, there are two conditions that must be met, two conditions which must be satisfied. And they are as follows. The first condition is that the force must act on the object as the object is being displaced. And the second condition is that the force must be in the same direction as the motion, or, to put it more specifically, the force must be parallel to the displacement. So notice, the force in case 3 was not parallel to the displacement of the object. If its initial velocity was up and the force was acting to the left, it was perpendicular. And so that's our clear differentiating criterion. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now we have a good question to ask here, now that we've looked at these two conditions for work. And the question is, how can we identify the force in the same direction as the motion when the force acts at an angle above the horizontal? So let's say here we have an object and its displacement is going to be to the right. And let's say the force acts like this. The force is not parallel to the displacement, but it's certainly not perpendicular. How do we identify the force in the same direction as the motion? While it is true that the force is not parallel to the displacement, a component of it is. And that's the key detail here. When a force acts at an angle above the horizontal, you must find the horizontal component of the force, because that is the force in the direction of the displacement. And you do that, of course, by using the equation fx equals f cosine theta. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Let's just write that down as a note because this is very important. Since the force has to have a component which is parallel to the displacement, work will change the speed of the object when the object is moving on a horizontal surface. This is going to come up at the end of this video and then in the next few videos, but this is very important. Since the force has to have a component which is parallel to the displacement, the work will change the speed of the object if the object is moving on a horizontal surface. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the equation. Okay, so let's take a look at the equation. Mathematically speaking, work is defined as the product of the force and the displacement. The symbol for work is an uppercase W. And the equation, as it says here, is pretty straightforward. It's the product of the force and the displacement. But of course, as we just mentioned, we're really only talking about the force that is parallel to the displacement. And so sometimes, including in the reference table, which I'll show you in a minute, the equation is written like this. I don't ever really want you to write that. That's kind of useless. The way that I want you to write it is to go back to what we said before. The component of the force that is parallel to the displacement, at least when an object is moving on a horizontal surface like this, is going to be the horizontal component of the force. And so what we'll say here for the equation is that work is F delta x times the cosine of theta. And in that equation, F is the force's magnitude. We're not going to really go nuts about the direction because the angle is going to take care of that for us, measured in newtons. Delta x is the displacement magnitude, measured in meters. And theta is the angle between the force and the displacement, which of course is measured in degrees. And so looking at the structure of the equation, we can see here that to determine the amount of work you have, you need to take the force measured in newtons multiplied by the displacement measured in meters. The cosine is a unitless quantity. And so that means we end up with units of Newton meters. And if we want to break that down, remember, I'll just do this up here. The Newton is a kilogram meter per second squared. And we're going to multiply that by a meter, which means we are going to end up with units of kilogram meter squared per second squared. That is really super annoying to say, kilogram meter squared per second squared. And so we call that a joule, named after English physicist James Joule. And so we can say here, I'll write this just over in the corner, 1 joule is equal to 1 Newton meter, which is equal to 1 kilogram meter squared per second squared. And lastly, we have to talk about something that is a little confusing. Most of the time in honors physics, when we were first learning about all of this stuff, I would ask you questions like, do you think that's a vector? Or do you think that's a scalar? And a lot of you probably came up with a perfectly reasonable way of attempting to answer that question. You would say, like, well, let's look at what that quantity is made of. You'd look at speed and you say, well, speed is distance over time, and distance is a scalar, and time is a scalar, so speed is going to be a scalar. And if you look at velocity, well, displacement is a vector, and since velocity is displacement over time, then velocity should be a vector. Force is a vector. Displacement is a vector. Work is a scalar, though. The reason for this is actually a little complicated. I'll just briefly say it, and you can look this up on your own. In upper level math, there are actually different kinds of multiplication. There are 2 kinds of multiplication specifically that have relevance in physics, and one of them is called the dot product, and the other is called the cross product. You can Google these if you want. And essentially, the difference between a dot product and a cross product is that a dot product takes a vector times a vector and spits out a scalar. Work is determined using a dot product. Whereas a cross product takes a vector times a vector and spits out a vector. And so this is the kind of multiplication that would take 2 vectors and multiply them and give you a scalar. Now, just very quickly before we move on here, I just want to show you, if you go to the AP Physics reference table, you will see here this version of the equation that says work is equal to the parallel force times the displacement, and then they write FD cosine theta. I do personally, along with a bunch of other teachers, think it is odd that in this reference table, they do not write delta x. They write d. I'm assuming that the reason they're writing delta x, or they're not writing delta x and they're writing d, is because really you're just interested in the magnitude of the displacement. And if the object is moving in a straight line, the magnitude of the displacement is equal to the distance. But the version of the equation I want you to use, at least when you're solving problems on homeworks and on tests, is this version of the equation. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at a problem. All right, let's take a look at a problem. This problem says here, a small child, while crawling, drags a toy 4.5 meters away from its starting point with a force of 2.0 newtons. Then, the child stands up and continues to drag the toy an additional 2.0 meters using the same force, but this time directed at an angle of 60 degrees. The question says to determine the total amount of work done by the child. As it says here on the top of the slide, I'd like you to not write down this entire question. I just want you to sketch a basic diagram showing you all of the details. So we'll draw the ground here, we'll show the box, and we'll say the box originally was displaced 4.5 meters. And it's going to end up there. And it's displaced by a force that acts like that. Then that force changes to act upward at an angle, and the box is displaced another 2 meters to end up there. And the question is asking us, what is the total amount of work done by the child? So I hope the text of the problem, and then especially the diagram here, make it obvious to you that there are 2 separate segments here in this problem. You have the first part where the force is acting purely parallel to the displacement, and then the second part where the force is acting at an angle. And so for the moment, until we make this point here, let's really just treat this as two separate problems. In the first segment here, we have a force, and that force has a magnitude of 2.0 newtons. That's also the force in the second segment, so let's just go ahead and write that down. The displacement in the first segment is 4.5 meters. And notice here, because the force is parallel to the displacement, and theta is the angle between the force and the displacement, that means the angle in this problem, or at least in this segment of the problem, is going to be 0 degrees. And we're looking for the work. Now, in segment 2, while the force is the same, the displacement is different. It's only 2 meters. And the angle between the force and the displacement is 60 degrees. And of course, we're looking for the work. And now, because there are two segments of the work, I'm going to go ahead and call this W2 and call this W1. So work, as we just said, and we'll call it W1 for work 1, is equal to F delta X times the cosine of the angle. And the angle in this segment is 0. So as I mentioned when we were first dealing with things being 0 regularly in problems, the cosine of 0 degrees is 1. And so that means there's no point in plugging it in, just like there's no point in plugging things in when they're equal to 0. And so we're going to put an arrow through this like we usually do when something is equal to 0. But since the cosine of 0 degrees is equal to 1, we're just going to put a 1 at the end of the arrow, showing that that thing is equal to 1. And of course, because F times delta X times 1 is just F times delta X, then we can just rewrite it like that. And so that means work 1 is going to be the force, 2.0 newtons, times the displacement, 4.5 meters, and that gives us a work of 9 Newton meters. Or, if you want to put it this way, 9 joules. For the second segment, on the other hand, similar idea happening here, same equation, obviously, but now we have an angle that's not equal to 0. So work 2 is going to be the force, 2.0 newtons, times the displacement, 2.0 meters, times the cosine of 60 degrees. Cosine of 60, in this calculation here, the cosine of 60 is a half. So essentially we have 2 times a half. 2 times 2 is 4, and then half of 4 is 2 Newton meters, or 2 joules. And now we have a pretty good question to answer here. We have work happening along 2 separate segments where the angle is different. How do we find the total work done in this situation? The answer to the question is not complicated. It all comes down, really, to this. Whoops. Work is a scalar. And so since work is a scalar, to find the total work, you simply add the individual amounts of work done on the object. That's it. We will come back to this to write that down. But just to show it, the total work here is work 1 plus work 2, which is 9 Newton meters. You could write joules here, plus 2 Newton meters, which is equal, of course, to 11 Newton meters. And that's it. Since work is a scalar, to find the total work, you add the individual amounts of work done on the object. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And that brings us to the last part of today's video, which is all about the relationship between work and energy. Now, it's important to realize the way that we are going to be thinking about these problems is fairly straightforward, but it's new. we are always going to be thinking about energy problems in terms of a system. And so it's going to be very important to define our system in the problem, which objects are part of the system, and then which objects are not part of the system. And there's a good reason why. We will do this eventually later on, so you don't need to write any of this down. I'm just showing you. A system can have a bunch of different kinds of energy: kinetic energy, gravitational potential energy, elastic potential energy, thermal energy, chemical energy. And the basic idea is the total energy in the system is just the sum of the different energies in the system. That's it. It's pretty straightforward. Energy transformations between different types of energy can happen naturally without anything happening from the outside. However, when the system interacts with the outside environment, which notice as it says up here is everything that is not part of the system, work is done. Now, you may remember this when it says work and heat here from chemistry, talking about work and heat being exchanged with a system. The basic idea is when energy is transferred within the system, there is no work done. But when energy is transferred from the environment to the system, we say that work is done. And so the definition here is pretty simple. Work changes energy. Furthermore, the work-energy theorem, which is a super important concept in this course, says the total amount of work done on an object or by an object is equal to the change in total energy. It's not that hard to figure out. Look at the last problem we just did. We calculated that that child did 11 joules of work or 11 Newton meters of work on that toy. What that means, according to the work-energy theorem, is that the energy of the toy changed by 11 joules. That's what we're saying. And so we can also say here, the work-energy theorem allows us to see the connection between forces, because the work equation has force, kinematics, and energy. Knowing how the energy of a system changes allows us to make calculations about the forces that are acting within the system, which allows us to determine the acceleration, thus giving us a bridge to kinematics. Take a second to pause this video here and write this down. At least just the top part, this bottom part you don't need to write down, but the actual definition of the work-energy theorem is critical. Take a moment to write that down, and when you hit play, we'll move on. Now, to write the work-energy theorem in the form of an equation is pretty simple. The symbol for energy is E, and so we are literally just going to write W equals delta E. We could also say, if you want, but I'm sure you know this by now, delta E is going to be E final minus E initial. It's important to realize the reference table actually already tells you that too. If you look at the reference table, notice I didn't show this part before, but they do show you in the reference table as well that W is equal to delta E. The work done on an object is equal to the change in total energy of that object. That's the point here. And so the work-energy theorem gives us a pretty good definition of work. Work is the change in energy. And it also gives us a definition of energy, though obviously it's not a good definition. We know what energy is, and this is about as best as we can define it. Energy is the ability of an object to do work. The ability an object possesses to do work. And the key idea here is that energy can be transformed from one form to another form when a force is exerted and work is done. That's very important. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the last idea for today. The last thing I want to talk about here is a little bit of a confusing idea, but it's going to come up in some problems we're going to solve tomorrow. And that concept is negative work. That seems confusing because we already said work is a scalar. But just because work is a scalar doesn't mean it can't be negative. We already know scalars that can be negative. Probably the most recognizable example is temperature. Temperature is a scalar. It doesn't have a direction, but it can be negative. The point is just that the sign doesn't tell you direction. So even though work is a scalar, it has just a magnitude, it can be negative. The sign doesn't tell you the direction. That, of course, is the key point here. And so now we have a pretty important question to ask. Looking at the equation, how would it be possible for an object to have negative work done on it? The equation, if you remember, is that work equals the magnitude of the force times the magnitude of the displacement times the cosine of the angle. Well, if the force in that equation is just the magnitude, it's not that. And if the displacement part is just the magnitude of the displacement, it's not that. And so this can be the only culprit for how work could be negative, the cosine of the angle. When does the cosine function become negative? Remember from math, all students take class? Or what do they tell you? All students take calculus? The cosine is negative as soon as the angle gets above 90 degrees. I want you to think about what that means, though. What that means is the object is being displaced this way, and the force is acting this way. The angle between the force and the displacement is bigger than 90. Look at that force. It's going in the opposite direction of the displacement. It's making the object slow down. And so when the force is in the opposite direction of the motion, the work done on that object is negative because the cosine of the angle will be negative. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So the point that we're making here is that when the force acts opposite the direction of an object's displacement, the work done on that object is negative. But of course, the big question is, well, what does that mean? Well, it means the object is slowing down. But what does it really tell you about what work is? Specifically, what does it tell you about the energy? Work is equal to the change in energy. So, if the work is negative, that means the change in energy is negative. And if the change in energy is negative, all that really means is the energy of the object decreases. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, that is it for today. That basically wraps up basic work content. Tomorrow, we are going to use a lot of this information to take a look at a series of problems and try to put this information to good use. Have a good one, everybody.